So here's an example of how to use the acoustics pressure module. So again, we got to figure out if we want to do this in 2D or 3D or 2D axisymmetric. I'm going to stick with 2D for the quickest return. But now we're going to use the acoustics module instead of the fluid module. Aeroacoustics implies high speeds. Elastic waves is not something we're going to deal with, so pressure acoustics sounds good. It'll explain here when you want to use it and when you don't. So that seems viable. And so there's only one option. Let's do that. Do that, and you can see that the one dependent variable is the acoustic pressure. You'll also notice that ACPR is going to be the name that they're going to use when talking about the variables. You have a number of different options for the actual study. We're going to do a frequency domain study. That is, we're going to look across multiple frequencies. And that should bring us into the model maker, where we can start making the model. So again, if we go to parameters, we can define all our parameters of a length of 10 centimeters. I'm just hitting the tab key, height of 6 millimeters. And it's probably good enough to start. So if we go to our geometry, we can do a right button click, just keep moving down the model builder list. We're going to add a rectangle of width, length, and of height. And we can build it, and you can see that looks good. I'm going to add a point too, so we can look at the pressure at a point, just like we did before. And let's do this at 95% of the length and 50% of the height. And it pops it right there. Looks good. Next, we have to do the materials, so we do a right button click. There's a number of different ways we can do it. I find the easiest is to just get the picker, do a search, and double click. So now we've got a domain defined. The walls are all hard boundary walls, and we've got air inside it. So right now, nothing will actually happen. We need to excite it in some way. So there's a bunch of different ways we can excite it. We can say, let's do a pressure excitation at this wall, and it's going to ask for a P0 here. So if we say use P0, it'll say you haven't defined P0 yet, so let's go to parameters and define a P0. Just like we did before, we can define this as, say, 50 dB, so that's 2 e to the minus 5 Pascal times 10 raised to the 50 divided by 20. And that gives us a small number. All right, so if we go back here, we can see that, and now know what P0 is. Lastly, we can run this for a single frequency, let's say 700 hertz. And we can hit run, and you can see it runs pretty fast. And at 700 hertz, we get a higher pressure here, but not very much greater than the pressure we're actually looking at. So what might make sense to do is sweep over a number of different frequencies. So let's go back here and say, let's go instead do a range from 700 in steps of 1 hertz to, say, 5,000. And again, remember, you want to do a lot of steps, because if you do too big a step, you might miss the resonant frequency. And in this case, the resonant frequencies are very tight. So there's no viscous damping or anything to spread it out. So you can see it's already done. So that's pretty good. We can go ahead and just say, let's actually look at what it looks like. So we can do a 1D plot of our solution for all frequencies. And we can just say, let's look at it at a point. And we're going to pick this point. And we can just look at the pressure. And if we plot that up, you can see a total acoustic pressure of a big positive number here and a negative number here. And that's because, if you remember, we talked in class, this actually gives you back a complex number. So we really should do the absolute value of this, and that'll give us the magnitude. And now it looks like you'd expect. There's your fundamental and your two harmonics. This is going to be different from the simulation, the fluid simulation, where we did RMS. If you remember, for sine waves, it's easy to prove that the magnitude or the maximum displacement is simply 1.4 or the square root of 2 times greater than the RMS. So you could divide this by the square root of 2 if you wanted to try and make it similar to the fluid simulation.